In this video, we are going to conduct subgroup analysis and multiple logistic regression analysis for binary outcome data using SPSS. So data set we use is cabbage.sav. And cabbage.sav contains the data from VA randomized trial of cabbage versus standard medical therapy in patients with stable angina pectoris. An outcome of interest for today's example is all-cause mortality at 6 years after randomization. And we use variable status 6. And dead is coded 1 and alive is coded 0. And primary study exposure is a treatment. Variable for that is treatment. And surgery is coded 1 and medical treatment is coded 0. And potential confounding factor or potential effect modifier in this example is whether patient had left main disease LMD. Yes is coded 1 and no is coded 0. Okay, so let's perform first unadjusted analysis. So we simply want to see effect of treatment on death, and we ignore left main status. Right, so we use cabbage.sav and go to binary logistic, regression, status 6 is a dependent variable and treatment is a covariate. Treatment is coded as 01, so we don't have to worry about pushing this categorical button. And let's click on option. And we want confidence interval. Continue and OK. So effect of cabbage quantified by odds ratio is 0.731. What does this mean? Odds of dying in 6 years is reduced by 27% with cabbage compared to medical treatment, although the p-value indicate that difference was not statistically significant. So what should we do now? So this is RCT, so we actually don't really worry about confounding. And so many people analyze data with unadjusted analysis. So one choice is you go ahead to write up your paper, say effect was negative. And although you might think there may be a subgroup of patients who still benefit from this surgery, and why don't we look at patient-specific effect, subgroup-specific effect of surgery? So what is a good candidate for that? The variable which indicates severity of disease actually is a good candidate for potential effect modification. So we are going to look at data separately for patient with and without left main disease. So you go to data and split file, and we split file with and without left main disease. So you put LMD here. And OK, and let's repeat logistic regression analysis. Okay, so any analysis you conduct from this point will be conducted separately for with and without left main disease. So you go to regression, binary logistic, and click OK. Okay, so this is a result within patient without left main disease. So effective cabbage is 0.846, and that indicates odds of dying is decreased by 15% with cabbage compared to standard of therapy. And if you have left main disease, among patients without left main disease, although there was no statistical significance. And if you look at data among patients with left main disease, and cabbage actually show a great improvement. So odds ratio is 0.303, indicating 70% risk reduction of death in 6 years if you have cabbage compared to standard of medical treatment, and the p-value is significant. Okay. So now, instead of combining these two left main specific odds ratio, you want to show the statistical difference, right? Whether these two numbers, two odds ratios, are statistically meaningfully different. which means when someone else conducts similar study in future, do they actually observe similar differences? Okay, so let's compute the p-value comparing between 0.846 and 0.303 and see those are numerically different. So to do that, you first have to unsplit data. So go to data split file and unsplit. Okay, and go back to logistic regression. Okay, so now we do put the LMD in the equation, and we need a cross product term between treatment and LMD. So to do that, you push shift button, okay, and then you can highlight multiple variables at the same time, and then you click this button, so that will create interaction term, cross product term. Okay, and you click OK. Right, so go to p-value for this cross product term, treatment by LMD. So this p-value indicate whether those two LMD specific odds ratios are different or not. So p-value is 0.043. So now you have statistical evidence for the interaction. Okay, so what we did is we computed p-value to see whether the effect of cabbage is different between patient with and without left main disease. Okay, is 0.846 different from 0.303? And that p-value is statistically significant, therefore, and we conclude that the LMD seems to modify association of surgery and mortality. So this is how we conduct interaction analysis using logistic regression. And let me explain what are the meaning of beta coefficient or odds ratio. In the model, you include interaction term because this becomes a little bit tricky. Okay, so you can't really grab 2.689, which is odds ratio for LMD. Say this is a main effect of LMD, or you grab this 0.846 and say this is main effect of treatment. Instead, this 0.846, okay, in the model you include interaction, okay, and odds ratio for each term, treatment itself, indicate odds ratio of treatment within the patient without LMD, okay, which actually matches with your subgroup analysis. Okay, so where can we get odds ratio of treatment within LMD based on this model with interaction? You don't really have 0.303 here. Instead, if you multiply 0.846 to odds ratio for interaction 0.358, and that become, okay, and that become 0.303. Actually, I did it the other way, but if you multiply this and it becomes 0.303. The another terminology, odds ratio for interaction is ratio between two odds ratio. One is odds ratio of treatment among LMD divided by odds ratio of treatment among non-LMD. So, statistical testing you did in this model is this p-value examine whether this ratio, this value is statistically different from 1 or not. Okay. So if the ratio of two odds ratio are the same, and we could say LMD specific odds ratio of treatment are the same, i.e. there is no interaction and there is no effect modification. Okay, so this slide summarized I just said. So when you have cross-product term in the model, interpretation of odds ratio or beta coefficient for each parameter become a little bit tricky. Okay, so odds ratio for the treatment term okay, indicate odds ratio of treatment only among patients without left main disease. And if you want to compute odds ratio of treatment among patients with LMD, left main disease, you need to multiply these two numbers. Okay? So that's how you can compute both LMD specific effect of treatment. So if you conduct interaction analysis, you don't really have to do subgroup analysis because this one big model can let you compute LMD specific effect of treatment. Okay, let's move on to the next example. So in this example, we use the same data set, but instead of using LMD, we use variable for diabetes, whether a patient had diabetes at the baseline. And we want to see whether the diabetes is potential confounder or potential effect modifier. Okay? So what we did is we split the data, okay, and we conducted analysis evaluating effect of treatment only within patient without diabetes, and that gave odds ratios 0.76, was not statistically significant. And repeat the same analysis with patient with diabetes, and odds ratio is 0.59, and it was not statistically significant because 95% confidence interval includes 1. So now we need to decide whether we proceed to analyze data for confounding or for interaction. So if you do confounding analysis, you pull these two odds ratio so that, and you may gain power. So then you might see statistical significance by gaining power. Or if you think these two are meaningfully different, clinically meaningfully different, instead of pooling, you want to show the difference between these two, then you proceed to interaction analysis. Okay, so that depends on your clinical judgment. Okay, you don't really need p-value to judge if this difference is clinically meaningful. But anyway, if you want to look at p-value, okay, this is how you do. So you create a cross terminology between treatment and diabetes, okay, and then you run the model with treatment itself, diabetes itself, and then cross product term, okay, 3 terms in the model. Check p-value for the interaction term, cross product term, and this statistically evaluate these two odds ratios are different. So p-value in this case is 0.6, which is large. So let's not try to detect the difference. So what you do is and drop interaction term from the model, and you adjust effect of diabetes. So you go to binary logistic regression. Okay, so instead of looking at interaction, to look at interaction, you need a model. Actually, here you need to push control button, okay, and then create a cross product term. And we saw this p-value is not, p-value for this cross product term is highly insignificant. So let's drop interaction from the model. And this analysis, you are only adjusting for diabetes itself, right? No cross product term. So that means you are pulling to odds ratio. So after you combine the two odds ratio become 0.732, and so this is diabetes adjusted odds ratio of treatment on 6-year mortality, and p-value did not change much compared to unadjusted analysis. So you conclude effect of CABG was not statistically significant, regardless of CABG, regardless of diabetes, or independent of diabetes. So what is the next step? Next step is we want to see whether the diabetes is really confounding result of CABG, effect of CABG. So what do? So we now compare two odds ratio. What odds ratio we compare? Diabetes adjusted odds ratio, which is 0.732, and diabetes unadjusted odds ratio. So that actually very first analysis we did, this one. So this is diabetes unadjusted odds ratio, which is 0.731, p-value is 0.081. So if you compare this 0.731 to this 0.732, and it's not different. So therefore, you may conclude diabetes is not confounding and nor effect modifier. So what we just did is, since when we split the data by diabetes, we look at diabetes specific odds ratio of treatment, and they are not meaningfully different. Therefore, we try to combine the two odds ratio, and after we combine, that provided a diabetes adjusted odds ratio of treatment, and effective cabbage become 0.73, and we wanted to judge diabetes was a confounder or not. Therefore, we compare diabetes adjusted odds ratio cabbage with unadjusted effective cabbage, and these two are not different. Therefore, we concluded diabetes is not confounding nor modifying effective treatment, or nor interaction. And this is in fact expected because in RCT, randomization provides similarity of distribution of diabetes between cabbage versus control groups. So confounding is rarely the problem in RCT. But as we saw in LMD example, effect modification can still exist in RCT. Effect modification is a biological finding, and it's not a bias caused by study design. And so I hope this video helped you to understand confounding versus effect modification, i.e. interaction, in the setting of randomized clinical trial when you have a binary outcome variable.